Here's questions asking, consider the basic BJT current mirror figure 8.17 for the case in which Q2 has m times the area of Q1. Show that the current transfer ratio is given by equation 8.19. If beta is specified to be a minimum of 80, what is the largest current ratio possible if the error introduced by the finite beta is limited to 10%? Okay, now let's see how to do that. Okay. Okay, first of all, if you don't look at the circuit, we have I reference, and this emitter part is connected to the ground, and VBE is equal for both of them. So we can say VBE1 is equal to VBE2. Okay, and for the VBE, we derived an expression that is VT ln of IC1 over IS. This is for the first one, so I call this one IS1 as well. This for the first one. That is also equivalent to VT ln of, here the current flow through this one is I0 over IS2. Okay, and from this one we can see that IC1 over IS1 is equal to I0 over IS2. Okay, and if we rearrange this equation, I0 over IC1 becomes IS2 over IS1. This is what we call this transfer ratio. That is equal to M. M is the transfer ratio, and that is the question is asking here. So here is the question is asking, if beta is specified to be a minimum of 80, what is the largest current transfer ratio possible if the error introduced by the beta is limited to 10%? So we have to calculate this M value when the beta is 80, and there's also error of 10% in the current. Let me double check that. If beta is specified to a minimum 80, what is the largest current transfer ratio possible if error introduced by the finite beta is 10%? Okay, so there's error 10%, and also the beta is finite, that is 80 value. Okay, these are the two things we need to know. And in order to solve this problem, first we had to look at the ideal condition, like when the beta is infinite, and when the beta is infinite. But before I go and do that, let's derive the equation first. So also, like here we have this equation, I0 over IC1 is equal to IS2 over IS1. That is equal to M, we see that. And if we just grab this part alone, I0 over IC1, that is equal to M. I0 over IC1 is equal to M. And if we rearrange this equation in terms of IC1, that is going to be I0 divided by M. Okay, and this is helpful because there's another equation for the I reference that is given by IC1. We are looking at this circuit right here. The collector current and the base current of these two should be equal to the reference current. IC1 plus IB1 plus IB2, and for the IB1, if we look at here, so if we want to write this base current in terms of the collector current. For this one we can call it IC1. For this one we can call it I0. Whatever this one divided by beta is equal to the base current. So we can use that instead of IB1 and IB2. So this IC1 plus base current of the first one is IC1 divided by beta, and base current of the second one is I0 divided by beta. And here we can take the IC1 common. If you do that, then this is the only term that comes with the common, so 1 plus 1 over beta, and this one remains outside, and keep the other term outside because nothing common there, plus I0 over beta. And we have another expression for the IC1 over here, I0 over M. We can substitute that one over here. If you do that, then this is I0 over M times 1 plus 1 over beta plus I0 over beta right here. Now we can take the I0 common, and if we can also take I0 over M common, but if we take the M common, then we have to multiply here by M because we are taking something common that's not there, so we have to multiply that. So 1 plus 1 over beta, and if I take the I0 common, this is just 1, and in the denominator we have beta still remains, and since we have M also there, so we have to multiply the numerator by M. Okay, and that is this, and since both of them have the same base, we can add them directly. Let's do it in the next page. So we are just deriving the equation for the I reference. I reference is equal to I0 over M divided multiply by here 1 plus beta is common, so we can take it as common denominator, so 1 plus M over beta. Okay, so we have this expression right now. Finally, we can derive something like I0 over I reference is equal to M over I0 over I reference equal to M over this value, that is 1 plus M over beta. Okay, and let's look at the ideal condition. Ideal condition is there is no error and beta is infinity. If it's that's the case, then this is M is equal to 1 plus M over infinity. Then this whole thing becomes 0, so M over 1. So we will end up getting I0 over I reference is equal to M over 1, because this whole thing becomes 0 because we are dividing 1 plus M over a large value, so that tends to become 0. And then from this one we can say that I0 is therefore equal to M times I reference. Okay, so this is the case right now, and this ratio has the error. Let me double check. If beta is specified to be a minimum of 80, what is the largest transfer ratio possible? The error into finite beta is 10%. So this one is going to have 10% error. So it means we can use this equation we derive right here. This one, we can use this one, but we have to take into consider there's 10% error. So let me grab that equation in a new page. I0 over I reference is equal to M over 1 plus M over beta. M over 1 plus M over beta. This is 1 plus M. Yes. Okay. So instead of I0, we can replace that one with this M times I reference. Okay, but there's a 10% error, so we are taking that one into consideration. So 100% minus 10, only 90% is going to be realized. So I reference, and then this divided by I reference, that's equal to m over 1 plus 1 plus m over beta, and this m cancels, this I reference cancels. We get 90%, that is in decimal 0.9, that's in fraction, that's 0.9, and here we get 1 over 1 plus m over beta. Beta is 80, and here we had to just solve for the m, and we will end up getting 7.89 value for the m. And that's how we do this kind of problems, and that is our transfer ratio. And that's it for this video. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys